So hi everyone, Happy New Year and welcome to the first meeting of 2022 for the Stanford Amateur Radio Club. Tonight we're going to have an invited talk by Matt Ettus, who's the founder of Ettus Research and creator of the USRP radio. And he's going to talk about MIMO communication and GNU radio tonight.
Okay. Hi, everybody. Matt, sorry to correct you, but Matt Ettus is the preferred pronunciation. It's good to see some familiar names here. So I'm going to give a talk that I originally gave for the GNU Radio Conference, which was back in September. It's actually more focused on the sort of the multipath aspects, and then MIMO and how to use it, and in particular how to use it within GNU Radio, which I'm of course a big fan of and contributor to. I'll get started here. My intention is that this is interactive, so shout out if you've got any questions or anything. The goal is communication. So the error correction is when you ask questions for what I say that's not clear. So I'll go ahead and get started and share my screen here while I figure out where the button to click to do that is. Oh, there it is. I got started with the Stanford Radio Club back in 1998. I realize now, which is a long time ago. I was not a Stanford student per se, but I was taking classes with the Stanford Instructional Television Network, which was basically they beamed microwave television to local companies, and I was working for Sun, and I got to take a couple of classes that way, and that's how I joined. I haven't been very active for quite a long time, but it's good to see that people are still going. I am going to shut off my video here if I can figure that out while I get started. Actually, perhaps that was not possible. Okay, well, in any case, I guess you'll have to look at me in addition to the slides. So anyway, the topic is MIMO and diversity and multipath. And my goal is to really share an intuition and a deep understanding of these things, rather than go through equations and stuff like are in all the books. So this presentation is actually pretty light on math, and it's mostly demos, and so hopefully that'll help help with understanding and give a better feel for how these phenomena and these techniques work. So start out with propagation and multipath, and I would assume most people here know this to some degree, but when we look at propagation, there's sort of three major components to the path loss, and which affects what you would receive at the receiving end of a communication. So first would be distance or spreading, and that gives us what we call the free space path loss, which is proportional to r squared. And it's actually it's useful not to think of it as a loss, but really as a spreading. And the reason for that is that there is no actual dissipation in this. This is just a spreading out of the power as it leaves the transmit antenna. Nothing is actually turned into heat here, but some of it may go in directions that are not useful. The next aspect would be large scale fading, and that consists of things like shadowing and absorption. It could be oxygen absorption. It could be absorption in a tree, which would sort of fall under shadowing or absorption. But oxygen absorption, water absorption, depending on the band you're in. Although, in most cases, you can ignore those sorts of losses, but the shadowing is important. And then we get to the small scale fading, which is you can attribute to blocking and multipath. And so blocking would be somebody walking in front of you, or as we would be concerned at my employer, holding your phone, your hand will often block one or more of the antennas, or holding the phone next to your head, you'll end up blocking antennas as well that way. And so there's a lot of factors that go into how strong a signal you receive. But the one we're most concerned with here today is multipath, which can be constructive or destructive and results from reflections and diffraction and these various paths that you see on the right side. And scattering is sort of like lots of little reflections, and then when you talk about reflection, it's often a specular reflection. But these sort of all work together to form one common phenomenon that we call multipath. So actually, let me go back here. So one thing to remember is that now all of these paths are actually longer than the direct path, and so will arrive after the direct path, or after the direct path would have if it is fully blocked. And that's something to keep in mind, and that can be useful. And that's how we one of the ways we characterize multipath. But the two major ways we characterize multipath are first, is it flat or frequency selective? And then on the other hand, where there is, which is sort of a time domain behavior. And then the other way we look at it is in the next slide, is constant versus time varying. So we'll start with flat versus frequency selective. So what causes fading to be flat or frequency selective? Well, as I mentioned, the delayed paths are the reflected paths are all arrive later than the main path. And can everybody see my pointer? Or good. Okay. So the reflections arrive later than the direct path. And now, so what that means is that you have the same signal coming back and interfering with the main direct signal at some time later. Now, if that time is significant, or sorry, I should say, the longer that time is, the more narrow you will see this effect in the frequency domain, right? If everything arrived at the same time, then it's like an impulse, and while it may fade because they're out of phase with each other, there won't be a frequency selective component. But the longer the delay is, the narrower in frequency this will be. So for example, if you had something that a signal that's 1 megahertz wide, and the excess delays are much less than a microsecond, then you can effectively consider your fading to be flat, even though on a large scale it might be frequency selective. For all intents and purposes, for your signal, it'll be flat. On the other hand, if you have tens of microseconds of delay, then you will see nulls within your signal, and so you need to treat that differently than just amplitude changes. So we model this with these tap delay lines, and really the question, flat versus frequency selective, is can we resolve those separate paths within this channel bandwidth? Now, frequency selective multipath needs to be flattened to in order to, or it needs to be dealt with in some way in order to effectively receive the signal. And so there's three main methods. If you have a sort of a single carrier system, let's say you're sending PSK or FM radio or whatever, you might use a conventional equalizer, and there's many topologies on that, and books and books on how to do that. But in general, what they try to do is invert the channel so that the places where there's a dip in the spectrum, you would have additional gain, and that would help flatten the signal out. Because if you don't flatten the response out, your symbol will be distorted. In addition to the noise, it'll have distortion. It'll be harder to recover. But there's two other ways that multipath can be a frequency selective multipath can be dealt with. And, the next one is spread spectrum. And the idea behind spread spectrum is you just spread the signal as wide as possible so that you can effectively average out those frequency nulls. And if you look at this in the time domain, what you're really doing is you're attempting to separately resolve all of these individual paths with what's often called a rake receiver, like as in the tines of a rake, and that allows you to actually constructively add those separate components to receive the signal, and so you've effectively both flattened and then taken advantage of the multipath in that case. But this implies that the signal bandwidth must be much wider than the null to null spacing, based on in order to, or conversely, the symbol rate of the channel must be much tighter than the number of than the spacing of the delayed signals. Finally, there's OFDM, which takes the opposite tact, which is to have many very narrow signals, so that any one of them will see an effectively flat channel, and then you just have many of them in parallel, and some of them will be stronger, and some of the channels that are directly on a null will be weaker, but ideally you would have either interleaved across them or use coding to make up for the weak channels, and so that's how you deal with the frequency selectivity. So there's three main methods. I'm not going to past this. I'm not going to be too concerned with frequency selective multipath, but that's the basic idea. Does that make sense? Okay. So now, if we look at this in the other axis, then there's the question of, is my multipath constant or is it time varying? And that's characterized by the Doppler frequency, or the ratio of the Doppler frequency to the symbol period, or the coherence time of the channel. And essentially what this means is that all of these, if we look at these time domain components here, how quickly are they changing? How quickly are their amplitudes and phases and delays changing? And so we can sort of divide this time fading in sort of three different categories. So first you have what I would call quasi-static, which is the channel varies between packets, but each packet will have a different fading amount, and so we sort of estimate it once per packet, and then it just applies throughout the duration of the packet. That's of course the easiest to deal with. And then we have slow fading, which is where the channel is effectively constant over a symbol time period, but it changes during a packet. And so this implies that you have to track that fading. And then finally, we have fast fading, where the channel varies significantly during a symbol's time. And so, and that introduces this Doppler modulation. You shouldn't really confuse this with Doppler as in from a satellite, where sort of it's predictable and there's a certain amount based on velocities. This is more, although they use the term Doppler, is not like easy to point to something and say this is moving at X miles per hour, although sometimes you will induce this by driving around in a car or something and causing your fading to change rapidly. So this is more about the components are moving so quickly that your channel is no longer time invariant. It's still linear, but if you remember from signal processing classes, pretty much everything's linear time invariant, and they don't talk about anything else. But so you still have a linear channel, but it's now time varying, and what that means is that it's effectively modulating your signal, and it often has this in terrestrial sort of applications, this Doppler modulation can have a spectrum like you see on the right side in that plot there. So we have constant versus time varying, and we have flat versus frequency varying. So the flat versus frequency varying, we talked about how you deal with it, and the time varying, again, it depends on whether it's static or slow or fast fading. Fast fading, of course, being the hardest to deal with in a communication system. So how do we model this? How do we analyze it? So if you look on the right side, we have a vector diagram showing sort of a dominant component and then all of these other components that are reflections. Now, you can see that some will add, so some will actually be productive and will help your signal out, and some will be counterproductive and sort of cancel with your signal. And these, of course, are time varying, and if they're delayed, you wouldn't see it in this graph. That would sort of be the third dimension, but there would be the time delay to them, of course. But the way we characterize this fading, whether there's significant time delay or not, and no matter how fast they're changing, one of the ways we characterize this is as Riceian versus Rayleigh. Now, both I know Rayleigh and I think Rice as well were really statisticians or probability theorists and not radio people. So these refer to the probability distribution of the magnitude of the signal. And so Riceian implies that there is this dominant component that is the direct path, and Rayleigh implies that there is no dominant component. So this would be, the direct path is blocked. And you see that, very often in cellular, for example, where if you can't see the base station, it's likely you're experiencing Rayleigh fading to some degree. And so in that case, there is no direct. So it's a good thing there's multipath, because otherwise there would be no signal. Maybe that's the glass half full way to look at it. But in any case, these two are characterized by this so-called K factor, where Riceian would have a non-zero K factor and Rayleigh would have a zero K factor. And then, of course, we have the Doppler frequency and the maximum excess delay, like we mentioned earlier. So I'm going to show a demo here in GNU Radio, and hopefully everybody can see the GNU Radio screen there. Thumbs up from anybody, William? Okay, good.
I think it's still the presentation.
Oh, okay.
I see the GNU Radio now.
Oh, you do? Okay, good. You had a little delay there. Okay, good. So this is the flow graph that I'm going to show in a moment, and this is for just plain old fading. So we have a noise source and a constant source, and throttle it because I'm running without hardware. This is all in simulation. Then I have a fading model, and we just display it on a histogram and a oscilloscope and an FFT. So here, and hopefully you guys can see that, I'm just going to turn off some of these factors here. So here I'm just sending a constant signal, and in the top you can see the amplitude of the received signal versus time coming through this fading simulator, right? And so right now here it is. This is I set the K factor to 0, so this is Rayleigh, and you can see it has this distribution, and this point here is 0 dB. So actually, very often the signal is actually stronger than the direct path would have been. And so this implies, and this is because there's multiple paths, and sometimes they interfere constructively, and so we actually do get gains sometimes with multipath. And one of the goals of MIMO is to make sure that you sort of are always operating over here whenever possible. So, but if you look at the top, you also have these very deep fades, sometimes as much as 40 dB, and that's this long tail of the distribution here. Now, as we change the Doppler frequency, you can see the higher the Doppler frequency, the closer they get together in time. And the lower the Doppler frequency, the wider it is. And of course, if I set the Doppler frequency to 0, it's just constant, and your distribution is a constant there. So that's not realistic. So let's set it here. So, and then now we have our K factor. So K factor, this is our Rayleigh fading, but as the K factor increases and as the direct path is more important, it becomes much more constant. You get much smaller fades. So this is a K factor of 100. This means you have effectively no no appreciable multipath, and you can see you get a very narrow histogram here. So that's sort of the that's the sort of characterization of the multipath. Now, if we look down here, I'm going to try to zoom in a little bit here. Okay, so this is what the signal looks like in the frequency domain. So if we set our Doppler frequency to 0, we just get our arriving signal, and everything's constant. And we set the Doppler frequency to something low, you could see the signal goes up and down in the frequency domain, right, as it fades in and out. Now, as we increase the Doppler frequency, you could see we actually start to create energy at other frequencies that were not what was sent. So that only happens either in a nonlinear system, which is not this, or in a time varying system. And so that's what we have here. This is happening fast enough to modulate your signal, right? And so this obviously would make it very difficult to detect. And so if you were using OFDM, you would be, yeah, so in any case, yes, you would need to use some way of flattening this out. One mechanism is shortening your symbol time. So this OFDM would not be the right way to do that. Is making your signal wider so that this becomes insignificant. So you would have to have a much wider signal. So in any case, that's with a high Doppler. I'm going to turn that back down, and I'm going to switch over to noise. And if you look at the signal here, and actually I'm going to turn the Doppler to 0, and you can see I average this out, and you can see it's all flat. And now what's the reason that it's flat in the frequency domain, even though it'll vary in the time domain, is because this is a non-frequency selective channel I've created. It's all 0 delay for all of the paths. So now I'm gonna close this, and I'm gonna switch over to the frequency selective fading model, which actually has a maximum excess delay in samples of here we have it up about 10 samples of maximum excess delay here. So I'm going to rerun this, and I won't do everything, but we'll turn on the Doppler. We'll switch over to noise, and then actually I'll turn the Doppler off, and actually let's turn up the K factor here, so we have, or sorry, turn it down so we have significant fading, and then I'll average this, and now you can see that there's frequency selectivity to the channel. You can see we have a dip over here and a dip over here. That's because we have that excess delay in the channel. Now, if I turn up the Doppler and then turn it back off, you can see that those dips have moved because it's in a different place now. Now, if the Doppler is high enough, it sort of all smears and you don't really see it, but it is a frequency selective channel, even though you can't tell it in this display. And a spectrogram would show that a little bit better. So, so I hope that made sense to everybody. I'm going to go back and go back to the slide deck here. So, so that's multipath. So now the question is, well, that's one transmit antenna going to one receive antenna, and so what can we do, right? If you're transmitting like that, and all of a sudden you're in a, or your receiver is in a null, whether it's in frequency or in time, no signal gets through. So around the late 90s, people really started to look at MIMO. Although the concepts have been around a long time, the goal of MIMO is to improve your results in a multipath channel like this. And how does it do it? It does it by building what we call diversity gains. So rather than just having, if you had one transmitter and one receiver, you would have this one path, this H11. But by having multiple transmitters and or multiple receivers, you build up a diversity of paths. So now if those paths have the same fading, it's not really that useful. But if they have, if they have different fading and hopefully uncorrelated or partially uncorrelated fading, then you can actually build up a more reliable system. And I'll show a flow graph in a bit that sort of shows how that works. But what does it mean when I say correlated? So if you have, if we go back to the diagram earlier of all of these paths, if you have a sufficiently rich set of paths, then moving an antenna or having a second antenna some distance away from the first can result in uncorrelated scattering. Now, what is that distance? It really depends on how much multipath there is. The more multipath you have, the with a wider variety of angles, the shorter that distance is. And in an ideal situation, it's, people say it's about 1/4 to 1/2 of a wavelength. But if there's not much multipath, you might have to move significantly further. Now, we're not talking about, sort of one path not being blocked by a car and the other being blocked by a car. This is more about these components, as you see here, sort of being at different relative phase angles because of the different distances that the two different antennas might see. So if we go back here, so very often you'll hear, you'll talk about correlation between the paths. And so that's what we mean by that. And so I'm going to show a quick flow graph here with MIMO. And hopefully everybody sees this one now.
Are you thinking that the transmitters are all on the same frequency, or is this optional?
So in general, in the vast majority of cases, the transmitters will all be on the same frequency. That's not to say you wouldn't want to potentially use different frequencies, but that is much less common. So what we're talking about here is getting spatial diversity by having multiple antennas, at slightly different locations. There is also frequency diversity, right? So if you had frequency diversity by using two different frequencies, then you're also less likely to have a fade in both of them at the same time. There's also, in the case of frequency selective fading, and OFDM would take advantage of that. There's time diversity, which is given by, ECC coding and repetition and stuff. And so most communication systems, you'll have all of these, although you don't usually have like really wide frequency diversity. Although with modern cell phones, you will often be in a mode that they call carrier aggregation. So you might be receiving a signal from Verizon on your phone on two bands at once. And when you have two bands at once, the fades on one band are likely to be very uncorrelated with the fades on another band. So that's another way to get diversity. And that's really the goal here. But typically when you say MIMO, you mean the same frequency and at the same time, right? Again, you could do it at different times as well, but typically you mean at the same time. Okay, so showing this here, we have the same signals generated, but now we send it over two different paths. And then I use this matrix multiplier to induce correlation between the paths. And then we have the same outputs as you saw in the previous diagram. So here, again, I'll turn on the Doppler frequency, right? And K factor. And so now if this is, you see one fade on the top, and I'm just sort of making it a convenient shape. Now, this is what you would see if the two paths are fully correlated. They have a correlation coefficient of 1. You could see that there's really no diversity. I mean, you get two copies of the same signal, right? You see the red and the blue on top of each other, and the histogram, of course, matches. But as you move the antennas apart, you can reduce the correlation. And again, the geometry of the situation will determine that. But here you can see, when one has a deep fade, the other one, it's pretty faded as well. but it's not exactly the same. And then as we go to perfect, complete decorrelation, you can see the likelihood of one having a fade of both having a fade at the same time is pretty low. And so this is the ideal situation. You rarely have the full decorrelation, but if you did, what that means is that you have what we call diversity. And so if you think about that, let's say the likelihood that you were in a fade on one channel was 10%, then the likelihood that you're in a fade on both, if they're completely uncorrelated, is only 1%. And so you can see that's actually can be a very big gain in terms of performance, right? And very often in fading radio systems, we talk about the outage probability, and so the math is easy. You can do in your head for outage probability, even if it's a little bit harder for bit error rate. Did I lose a graph there? Oh no, there it is. Okay, so in any case, yeah, so that's the MIMO fading, and that's sort of a demonstration of how it works. So now I'm going to talk about MIMO radios and how you would design radios to deal with this. So this is sort of a canonical diagram of a digital communication system. You start with source coding. That might be your MP3 encoding, and then your channel encoding. This is your, let's say, turbo coding or LDPC or ham encoding or something like that. Then you modulate. You have your MIMO encoding. This is the new part here. Channelize, and then you have your propagation and path loss, and then you have noise. And you notice I put the noise on the receive side, because the noise is really actually a receive phenomenon, right? So we don't pass the noise through the channel, and that's important for modeling. The fading happens first, then the noise is added. And then you have time and frequency sync, dechannelization, despreading, right? All of the standard stuff is in your comm system. The part I'm going to talk about today is the part in white. I'm not really going to go into the dark parts. We'll assume this is the exercise left to the reader, assume the signal is perfectly synchronized and all that stuff that doesn't happen in the real world. I'm leaving that part out. We're just going to use perfectly synchronized signals, and we'll be looking at the modulation, the MIMO encoding, the propagation, the decoding, the demod. So what are the MIMO techniques that we can use to take advantage of these multiple input, multiple output channels? It's one thing to say, okay, I'm going to transmit on a bunch of transmitters and receive on a bunch of receivers, but how do we actually do something useful with that? And first, the question is why? Well, the goal is increased reliability, and then the next level is increased throughput. So the increased reliability, we can effectively get antenna gain and path diversity. And so that will help us during those fades. And actually, sometimes, if you get enough diversity, you can always be on that side of the histogram where things are better than if there was no multipath. And in fact, well-designed MIMO systems will actually take advantage of that, and you'll end up with better throughput and higher throughput and more reliability than you would have if there was no multipath. So it's taking the lemons and making lemonade, I guess, and getting that increased throughput. So now, why wouldn't I want to use MIMO? Well, there's more hardware, right? You have multiple receive chains, multiple transmit chains, processing complexity. Some of the more advanced MIMO mechanisms require the sending of channel state information between both ends, and so there's some overhead with that. And in the absence of multipath, if you're going to have multiple antennas, you actually really just want to make them into a phased array antenna. You really only use the sort of conventional MIMO techniques when there is multipath. In the absence of multipath, they will sort of degenerate to just plain old phased arrays. Okay, so and actually, sorry to go back to that. So certainly if you look at the EME station at the club at the shack, which I assume is still there, there's arrays of Yagi antennas, right? I think there's an array of 16 Yagis on one of the bands. Now, those are all phased in an analog way, and so that we would call that a phased array. And that's the ideal in the absence of multipath. But if there were a multipath somewhere between here and the moon, you would actually be better off individually receiving on those antennas and then processing it digitally rather than using the analog hardware to do the beamforming. Okay, so MIMO techniques I would sort of divide into these 5 categories. First, we would have receive diversity, and the main choices there are antenna selection, equal gain combining, maximal ratio combining, and actually this reminds me of sort of my first exposure to MIMO, which was as a little kid going in my friend's parents' car, driving me home from his house. It was a brand new Buick, I remember, and it had 2 LEDs on the FM radio, and they would one would light and then the other, and they would sort of alternately flash back and forth randomly. And I asked what that was. It turned out it was telling you which of the 2 antennas on the car was being listened to at any one time, based on some sort of metric of which one had a better signal. And so that was some very early MIMO. This was like mid 80s. So this wasn't using any sort of fancy MIMO, but they had some mechanism of selecting the stronger antenna. So that is still used today. It's called antenna selection, and it's certainly one type of receive diversity. But the equal gain combining or the maximal ratio combining will have better performance. There on the transmit side, there's antenna selection again, or maximal ratio combining. Now, in order to do this on the transmit side, the transmitter has to know which channel is better. Now, on the receive side, that's easy, right? The receiver, has the received signal there, and if one is better than the other, or it can choose which one to use. But on transmit, you don't know that, and so that would imply some sort of channel state information being sent back to the transmitter. Now, there are some other ways this is done. If you happen to have a bidirectional transmission in a sort of on the same frequency, let's say time division duplex, cellular, then the transmitter can use the measurements that its own receiver took the last time it was receiving, and then know which antenna is probably better. But if there's a high Doppler rate, that information is not useful anymore by the time you're using it, right? If the channel is changed by the time the transmitter is doing that, that's not helpful. But if the channel is constant enough, then it can be useful. Then as you go further, there's these more complicated methods, space-time coding. There's what I would call true MIMO, where you do things like spatial multiplexing or pre-coding, and you can start to have multiple parallel data streams. And then finally, there's massive MIMO, which is sort of where you have 16 or 32 or 64 antennas, and it uses some different techniques, although they're sort of have the same basis as some of the others. And I'll go into examples of each of these. So this is a look at receive diversity. So you can see in the plot on the right, this line here. This is what BPSK would do in the presence of just plain old Gaussian noise and no multipath. But if you have multipath, then you end up with this curve here, this fading curve. And now so in addition to being requiring a higher SNR for every bit rate, you could see it actually, it's also less efficient, right? Here, if you're on the regular Gaussian noise curve, a dB or two can make a very big difference in bit error rate. But if you have regular fading, those dBs don't go quite as far, right? Here, up here, you may be 5 dB apart, but down here, you're 20 dB, 25 dB apart. So why is that? Well, if you think about what I was saying before about outage probability, if you have if you have an outage probability of 10%, where you get a fade that's like 40 dB deep, then 5 dB of additional power doesn't help. You still have a fade that's almost 40 dB deep, right? And so the probability of that fade occurring is still pretty high. Is still basically the same. And so that's why you sort of lose that steep nature here. Now once you have a line here rather than this rapid drop off, it becomes very inefficient to add more power to maintain that same bit error rate, right? If you have to up the power of the transmit power of your cell phone by 25 dB, that's just typically not possible. And so you have to instead back off in data rate. And so what diversity does is it allows you to fix the slope of that, right? So this would be two-way diversity. Oops, lost the page. Yeah. So this would be two-way diversity, and this would be four-way diversity. So in addition to sort of reducing the power, the power necessary for the bit error rate, the important part is it much improves that slope. So why is it improving the slope? Well, we said before, like if you have two-way diversity where each has an individual outage probability of 10%, you now drop down to 1%, right? But if you had an individual outage probability of 1%, now you're, that's 1 in 100, now you're 1 in 10,000, right? And so it goes with the square, and so that's why you get this steeper curve. And it would be the fourth power with this. And so in a logarithmic power graph like this, it changes the slope by the order of the diversity. And in fact, the way, if you were writing a paper for the IEEE and you wanted to show that your system has a certain order of diversity, you would effectively take the slope of this line to prove that that result. And so now, if you had infinite diversity, you would get back to this Gaussian here. So, in these fading scenarios, the diversity order affects the BER. So the easiest way to get some diversity is to use received diversity, and the easiest way is really this antenna selection. So this implies either some power detector or some fancier way of comparing the magnitude and choosing the stronger signal. And that's your output that goes into the rest of your receiver. Now, if it was, for example, in my friend's car or my friend's parents' car, switching back and forth, you would need to track the carrier, of course, otherwise you would hear a glitch, when you switch, or if it's in the middle of a packet, you would have some other issue, but that's relatively minor. So this is sort of the method of diversity. Then we have equal gain combining, which is where you just sort of add the two signals together. Now you have to track their carriers because in general, they won't just have different amplitudes, they'll also have different phases, right? All the plots I showed earlier were just showing the amplitudes, not showing the phases, but they have different phases. So you can't just add them together if they're out of phase, or you're just creating more multipath rather than less. But once the phase is tracked, you can add them together. And then there's this what's called maximal ratio combining, which is effectively the same thing, except it's a weighted combination of A and B. You weight it by how strong the channel is. So if A is coming in twice as strong as B, you then double A again and versus B, and you add them together. So what this does is it can be proven to be the optimal way of combining, but what it does is it makes sure that if one signal is really weak and the other is strong, you'll effectively mostly be using the strong signal, and you won't be adding in noise from the weak, right? In this situation, right, in equal gain combining, if A is good and B is effectively completely blocked, you don't gain any additional signal by adding these together, but you do gain additional noise. So equal gain combining in some situations where A and B are of different magnitudes can actually be worse, right? Because you're adding noise and not adding signal. Whereas maximal ratio combining would fix that. If B was 0, then this gain of B would also be 0 and it wouldn't get added in, and you would just be using A in that situation. But in any case, but this is a little more complicated because you have, in addition to tracking the carrier, you now have to estimate the SNR. So that's that's more DSP. Now, maximal ratio combining is equivalent to beamforming in the absence of multipath. So if there's no multipath, this is how you would form a beam between two, with two antennas. You would effectively be pointing at the transmit. With multipath, it's sort of you're effectively pointing a beam at proportionately at the two rays that are coming to you, to the receiver. And so so we don't really draw the ray diagrams in a multipath environment, but in the absence of multipath, there is a direction. So I'm going to show a flow graph that kind of demonstrates.
If I could jump in.
Yeah, go ahead.
So 2 meter EME, we are receiving the horizontal and vertical phases on separate receivers, but an interesting thing happens because the receiver doesn't know how strong the signals are until it decodes, because they're all at or below the noise level.
Mm-hmm.
So people are setting up like 6 LINRADs to decode all the phases and right circular and left circular, and then just a human picks the best decode.
Yeah, so that's probably not the most efficient way to do it, but yeah, that's using, you're effectively you're trying to receive linear but unknown linear polarization there. And so a lot of the math is the same as here. I wouldn't really call that, I mean, there is such a thing as polarization diversity, but in this case, that's more of a just, you're trying to compute the polarization. So a lot of the math ends up the same. So so I'm just going to show a couple of short flow graphs here. So this is the equal gain combining, right? What it looks like in GNU radio, right? You just adds the two signals together. You have to have already recovered the carrier at this point. There's maximal ratio combining, which of course looks a lot more complicated, but really what it is you're measuring SNR with these RMS blocks and then scaling the incoming signals proportionately and then adding it together, and that's what comes out. And then selection combining, basically this piece down here is attempting to determine which signal is stronger, and then it essentially controls which signal you end up receiving. But that's how they would be implemented. So this is a larger flow graph, but we can see we have just our constant source. We're sending data in this case through a correlated Rayleigh-Ricean channel, and then we're doing carrier detection here, right? We mux in the instead of doing a regular carrier, I'm doing it in time. So we're doing pilot symbols. So we mux in the pilot symbols, we take them out, we put them through a PLL to recover the carrier. We use the carrier on the data part, and then we will send the data out to the constellation display, and then we'll have, and actually we'll start out with just the 3 signals. So one that's received on one antenna, one that's received on a second antenna, and then the third one will be the output of, in this case, equal gain combining. And then we'll come back and I'll modify it for to show you all of them. So just so we see here, I'm gonna add some fading, give us a little bit of Doppler, and there's some noise. Now I'm gonna turn the noise down a little bit. So right now you can see 3 things. One is the blue is one path and the red is the other path, and you can see that they're actually uncorrelated. If I turn on the correlation, of course they match, and then green is the sum of the 2, and then I've divided it by 2 so it doesn't get bigger, right? So so it scales it. But you can see with this equal gain combining that sometimes the red is bad, sometimes the blue is bad, sometimes they're both good. But the green is typically pretty good because even if the red is bad, the blue's okay, and so the green tends to be better than the green is always better than the worst of the 2. Now, but even if we turn up the correlation, so they're the same, and I'm going to turn off the Doppler so I can zoom in for you here. I'm going to just zoom in here, and you can sort of see that the green is actually still better, right? Even though this is fully correlated, you actually get a little bit of gain because the green cloud is smaller, right, than the red or the blue clouds. And that's because even though the signal, even though the signal levels of the red and the blue are correlated, their noise is independent because they're using independent receive channels. And so you do get gain versus the noise here. You don't get the full antenna gain because this is equal gain combining and not maximal ratio. But you actually get receive gain. In addition to diversity gain, you get receive gain. And that's why the green cloud is smaller here, even in correlated noise. Now, when it's decorrelated, right, you can see also the green cloud has less noise than the red and the blue. Okay, so now I'm going to close this, and I'm going to this is going to be the same thing, but it's going to display two more. One is the maximal ratio, and one is the selection combining. And it's a little busier. That's why I started with the other one first. So here I'm going to again.
What are the vertical and horizontal axes here?
Oh, sorry. This is effectively voltage of the demodulated signal. These are constellation plots. So this is BPSK. So so you can see if I turn off the noise, you could just see the dots that were sent. But if we turn up the noise, that's sort of like a realistic communication system. So we have, so I'm going to make the fading a little worse here, right? So now the colors of the red and the blue are still the direct are still the two paths, and then the green is the equal gain combining, and the purple is the maximal ratio combining. And you can see that, let me turn off the Doppler so it's constant. You can see that the green and the purple is actually scaled differently, but you can see the purple actually has the smallest cloud, right? And that's because the maximal ratio combining is more intelligently adding this blue and red together, right? And the light blue is on top of the blue because the light blue is selection combining. So it's saying, oh, the blue is better than the red, so I'm going to be the light blue. I'm going to be on top of the blue. And I hope this is coming through on Zoom as clearly as it is on my screen. So again, we've got red is the currently worse faded signal. Blue is the better faded, less faded signal. Light blue is the selection combining has chosen that one. Green is the equal gain combining. This is where it's added then together and scaled it. And you can see the noise cloud is somewhat smaller than the two other noise clouds. And then MRC is purple, is scaled a little bit differently, but it has the smallest noise cloud of all because it's the most efficient receiver. And it's effectively getting antenna gain in addition to diversity gain. So if we go back to the presentation here, you can see now this plot, right, this shows the diversity gain, but this actually doesn't have the antenna gain, right? Because this is an academic paper, they subtract off the antenna gain. But in reality, with the antenna gain, it would also move these downward to the point where they became better than the Gaussian because you have received energy coming into two different antennas. So that's received diversity. And now I showed it with two receivers, but you can actually have any number of receivers that you find practical in a system. And in fact, again, speaking from the cellular world, LTE, most LTE phones had at least two receive antennas on most bands. And 5G phones and the newer LTE phones typically had either 2 or 4 antennas on most bands. The more common bands would be the ones where you have 4 antennas. And so you would have 4-way receive diversity at the very least. I mean, it often uses more complex mechanisms as well, but you would have 4 receive antennas. Typically, most phones up until the last couple of years did not have transmit diversity or transmit MIMO. They were receive only. So it would transmit on one antenna and receive on 2 or 4. They did have selection choice on some phones on transmit. So you might choose which antenna to transmit from, but for the most part, it always transmitted with the same one antenna. So now we get to transmit diversity. And so this is an additional mechanism that you can use, and you can of course use antenna selection. The problem with antenna selection is it gives you the diversity, but it doesn't give you antenna gain. And it still requires a channel state feedback from the receiver. But it gives you the same diversity gain. So actually there's no need for me to really show another flow graph. It would be the exact same flow graph. You get the same gain by doing transmit diversity. Now, if you're if you use maximal ratio transmission, MRT, which is the complement of the maximal ratio combining MRC on the receiver, then you're actually transmitting from two antennas or multiple antennas at once. And that's typically called transmit beamforming. And of course, requires the channel state feedback in order to do that. But this actually provides antenna gain and diversity gain once again. Now, it also requires, when you're making a comparison, to the fair comparison is if you're using two antennas, you divide the power to each of them by 2. Because you're putting the same amount of energy into the channel. But if you're limited by the power of your amplifier, you get another gain because now you have 2 amplifiers, right? If you're limited by the rules that say you can transmit 1 watt, then you would have to use half watt on each antenna. But if you're limited by how big an amplifier you can make, you actually get another 3 dB from having now 2 watts, 1 on each amplifier. And so this is exceedingly rarely used in amateur radio, but is becoming more common as I say, on the newer phones. You'll start to see phones that will transmit on 2 antennas at once. And this, of course, requires feedback from the network in order to productively do this, because you have to know, essentially the relative phase and relative gain of the 2 channels. Otherwise, you're going to interfere with yourself. And because you're effectively asking it, okay, am I pointing, you're effectively pointing in the right direction. That direction might not be towards exactly towards where the base station is, but you're pointing towards the strongest path, towards, or some function of the strongest path towards the gateways. So that's maximal ratio transmission, and so for TX diversity. Now we can go beyond that. And actually, so I should say, going back, you can do TX diversity and RX diversity at the same time, and that would be a 2x2 system, right? You do 2 transmissions and 2 receptions at once, or 3x2 or 2x4 or whatever. And again, modern cell phones have 2 or 4 receivers, but the base stations will have 2, 4, 8, or sometimes up 16 or 32. It's getting to be antennas at the base station side. Now, the base station being elevated above the ground some amount, they actually have to separate their antennas further apart than you would have to separate them in the phone. The closer you are to the multipath, the less you need to separate the antennas in order to get that decorrelation, right? But the tower is above most of the close-in multipath. It's relying on the multipath that's near you, and so in order to get decorrelation, they have to be spread significantly further than whereas on the phone, it's just you can spread them to opposite sides of the phone and get some amount of decorrelation. So what other mechanisms are there to get to use MIMO and to get the improvements in the channel that come with that? Well, the first is called space-time coding, and this is employed at the transmitter, and it allows the transmitter to get diversity gain without knowing what the channels are like to the receiver. So that's useful if there's no feedback, or it's a one-directional system, or you just want a simpler system. So it gives you diversity gain, but it can't give you antenna gain because it doesn't know which direction to send the energy. So instead, it sends 2 separate signals on the 2 or 3 or 4 different transmit antennas. So the most basic way of doing this is called Alamudi coding, and this was, I think, the paper is from '98, but it's very simple. You essentially you take your signal that you want to send, you take 2 consecutive symbols, and you multiply them by this matrix, right? So which is you're essentially sending one symbol, the other symbol, this is one antenna. So one row is one antenna. So that antenna would send first symbol 1, then symbol 2. The other antenna would send negative, the complex conjugate of the second one, and then in time 2 would send the complex conjugate of the first symbol. So now this seems weirdly complicated, but why do they do that? So what this means is that you're transmitting on 2 antennas and you get no loss in data rate and you get full diversity. And so this is actually a really nice property because now you get diversity in transmit without having to know anything about the channel and without having to know, without having to slow down. Unfortunately, this doesn't generalize beyond 2 antennas, but there are ways to sort of extend it that give up one of the factors. Either it's not fully orthogonal, or you don't get full diversity, or you lose a little bit of data rate. And so this is actually used in Wi-Fi. In the more modern Wi-Fi systems, they have with 2 antennas, they have Alamudi coding as one of the many modes, and they have extended Alamudi coding with when you go to 2 or 3 or 4, 3 or 4 or 8 antennas. So I actually have a demo of this, and one interesting aspect of Alamudi, which this is the encoder, right? This just encodes that matrix math that you saw. One interesting aspect of this is that you don't need multiple antennas on the receiver, even though you're transmitting 2 different things from the 2 transmit antennas. And actually, you can receive it with a single receiver. You could also have multiple receive antennas, and then you would get 4-way diversity, right? Because it's the product of the 2. But that's not strictly necessary. So here we have the same thing, but instead of we have our separate channels. This is the Alamudi encoder in front of it. So it encodes the 2 different streams over the 2 different channels. And then we have our receiver. So first we have an estimator, and the estimator goes into the estimation port of the receiver, and we have the data bits go into the receiver as well. And we'll see the constellation as received. So what we see here is in the upper, this is the path. This is what the receiver has estimated as the 2 paths. So you can see we have 2 paths are set to 1 and 1 here, and so it's scaled, but it's 0.5 on both of them. Down here, we're showing the red and the blue. The red is the decoded signal, but what's more interesting is the blue. The blue is what the receive antennas see. So you can actually see that you're no longer receiving just a BPSK because you've done this coding, and now you're receiving 2 different transmitters at once. So one of them has this, and they add together right at the receiver. So you're actually seeing +1, -1, 0, and +1 because those have added together and been received. But the decoder is able to separate them out into this 1 and 0, the 2 red clouds. So now, but we can vary the channel, right? And you can see that now the blue has bifurcated on the receive side, right? You get these 2, you get these 4 points because the 2 different paths have different gains, right? So the receiver sees these blue things, these 4 blue things, and by using math and this channel estimation is able to correctly receive the 2 red clouds here, right? So you can see we can move these around, and we're still able to receive. Now, in the case where one of the paths is 0, and I'll set this to 0 here, right? One path is 0, and so you can see the estimation is right around 0. We're still able to decode, right? Because we're not trying to send any extra bits. So if either path fades completely, you can see we still get the correct reception here, but the noise is amplified. Now, as the second path also fades to 0, this would be, okay, if both of them have really bad paths, you could see the blue goes into the middle and the red just explodes, right? Because we have essentially nothing arriving. So you're right, it's not magical, it's not a miracle, it's not gonna receive when there's no signal, but if either one of them is non-zero, we're able to receive. And so that's our path diversity, right? One of them gets a horrible fade, it's okay, the other one gets through, right? That's the essence of diversity here, right? As long as one gets through, we're okay. Or some combination, even if they're both very weak, the combination works. So now I'm going to switch over from these hand-controlled channels. I'm going to give it back to the fading simulator, and I'm going to set the Doppler on it so it moves around, and set the K factor to something not so great. And you can see these are two channel estimations. You can see the two channels are mostly independent of each other, right? The correlations they are independent of each other. The correlation is low. K factor is high. Sometimes they seem to follow. Sometimes they don't. And so you can see the blues are moving around because that's what's received, but the red still is received. But every now and then, when both of these go towards the center, the red explodes, the noise gets amplified. And that's because the estimation process is essentially becoming a singular matrix, and the math explodes and the noise is amplified. But as long as there's one path that's decent, that doesn't happen. Okay, so I'm getting near the end of, that was the last demo. The more advanced MIMO, there's methods like pre-coding, which is, essentially that's the receiver is told by the transmitter the transmitter is told by the receiver what the path looks like, and you are able to design the signal to effectively invert the path and maximize and produce multiple separate parallel channels. And so this allows you to effectively you have these what I would call eigen channels, where you if you have a few good eigenvalues, you can direct the energy of your transmissions into those eigenvalues so that they're received at the receiver strongly. And so you can create these parallel channels based on the minimum of the number of antennas at each end. So if you have two on each end, you can effectively create two completely independent channels as long as there's sufficient multipath. Now, if you have 8 on one end and 4 on the other, you have 4 independent channels, and then you can use the extra antennas for diversity or to serve other users. And that's often the case, like when you have these 8-way cellular base stations and a 2-way antenna on your phone, it's able to create 2 parallel channels to you, but it can also create 6 parallel channels that go to other users. So that would be multi-user MIMO, and you may have seen like MU MIMO on your Wi-Fi router, and these are all features, and this is sort of what it's doing under the hood. And then there's another method called spatial multiplexing, and this one's really interesting. This is actually a little simpler than pre-coding. And what this is saying is, this is just saying, you know what, I don't know what the channels are between the transmit and the receive. I'm just going to send a different signal on each antenna and let the receiver figure it out. And this is spatial multiplexing. This is also a mode that's in Wi-Fi. If there's sufficient multipath that with low correlation, this actually works really well. If there's not great multipath, then typically the pre-coding will work better. But if there's sufficient multipath, then you can just send one set of bits on one antenna, a different set of bits on the other, and let the receiver sort it out. And then this uses a technique called sphere decoding, and it's also really interesting. I'd love to do a demo of that at some point, but we're mostly out of time. So those are the 2 main other techniques. And if you look at the sort of the 5G specs and the Wi-Fi specs, all of those sort of more advanced MIMO modes they have are some combination of pre-coding, spatial multiplexing, space-time block coding, which I already talked about, and diversity, right? And those are the basic building blocks for all of the more complicated MIMO systems. Finally, we have what we call massive MIMO. And if you look at the picture on the right, this is actually a setup. Back when I was at Ettus Research, we sold this system, or many of these systems, where a big pile of usurps to create 128 antennas, 128 RF streams, which then went to, in this case, these antennas on this patch array. And this is an active area of research, and it's at this point is starting to get deployed into cellular networks. And the idea is you have so many antennas at the base station side that you're able to create little clouds to each user individually. And now, if there was no multipath, you would just be sort of creating a fan beam towards them. But in a rich multipath environment, rather than having a beam in the conventional sense, you create a little cloud that is around the receive antenna. And so this is a highly asymmetric system, right? You'd have 32 to 128 antennas on one end, but the user typically only has 1 or 2 antennas. And this effectively gives a private little network for each user. And so it can drastically increase capacity of the network because you're reusing the same frequency at the same time to all of these users. Now, it's, of course, everything has a limit. And so the number of these clouds is some number smaller than the number of antennas at the base station. And it's dependent on a very rich multipath environment. And also each user has to send a lot of pilot signals. And so it's not magical, but this system on the right was used to demonstrate 160 bits per second per hertz, which at least at the time was a world record in terms of spectral efficiency. If you think about, BPSK, QPSK, you're talking 1 or 2 bits per second per hertz. And or if you go up to QAM 256, you may have 6 or 8 bits per second per hertz. So and normally as the number of bits per second per hertz rises, the power grows exponentially. So you might, if you weren't using a MIMO system, it's fundamentally impossible to send 128 bits per 160 bits per second per hertz. You would need more power than the sun can put out. But because it's not one channel, you have many parallel channels, you're actually able to do this. And it's a really powerful demonstration that these folks put together. This one in particular was at Lund University. And of course, I don't have a demo of this one. There'd be a lot of equipment for that. But these systems, now this was about 8 or 9 years ago. This was in the early days of massive MIMO. And this was the first massive MIMO over the air proof that this actually really worked and wasn't just math. These days, you're starting to see 32 antenna cell phone base stations, and they don't do quite as well as this research system because they are operating within the LTE standards and within the 5G standards, but they drastically or can drastically increase spectral efficiency. So in any case, so that's what I've got. Does anybody have any questions? And while I'm at it, I am recruiting for positions in comm systems and SDR and software engineering at Apple. So if you're interested in any sort of intern, full-time, whatever sort of job, let me know. But otherwise, I'll take any questions if anybody has any.
Matt, one thing you might comment on, this is something that hams have a greater understanding than most other folks because they've experienced it. And I wonder if you've actually seen that in your own experience or in the experience of, this multiple input, multiple output system is something that you wish you had when there's fading and you only have one antenna and there's more noise or more interference that you can deal with. So do hams have an advantage in what you're looking for?
Well, I mean, in terms of understanding, multipath, I think hams, unless you've listened to a signal, you really don't get it, right? I mean, like I gave this talk a couple times, and giving it even to people who understand all the math, if you've never listened to a radio, and particularly like a linear modulation like SSB, you don't really get it. And actually, one of the ways, actually, let me, I forgot to run one of my flow graphs here, but one of the ways I demonstrated it was with audio, because I do think that that is, very instructive, right? When you can hear the fades, it really, it really gives a much more solid understanding. So yeah, hams, I think, especially hams who use HF, really understand multipath and frequency selectivity and things like that. I do wish we saw more MIMO, or at least receive diversity usage within ham radio, but we really don't see it very much. I guess, with the analog modes, people tend not to do it, but every now and then someone who has a big plot of land will have 2 receive antennas, and do and sort of sometimes listen to one antenna in one ear and one antenna in the other ear, and do sort of human MIMO that way. But these techniques are really powerful. I mean, if you remember the plot that the BER plot, right? I mean, people would when we were doing packet radio would just keep turning up the wick, and they were fighting these 40 dB deep fades, and you're just not gonna, with any reasonable amplifier, you're not gonna burn through the fades. Really, what you need to do is use diversity, and so we use, the simple diversity is sort of time diversity and error correction coding. But if you can use antenna diversity and spatial diversity, it's free, and it gives you saves you a lot of power. And so yeah, I wish there was more of that. But now, I mean, really all the SDRs, or not all, but a lot of the SDRs now have MIMO capability. So if you look at, like, I mean, every USERP that I ever sold back to 2005 when I first started selling them, they all had MIMO capability. But I would say 99% of them, nobody ever used the second channel. But certainly, I mean, that's part of why I developed the USERP in the first place, was I wanted to experiment with MIMO communications. It ended up taking off and becoming a business, but really I just wanted to play with MIMO and OFDM. So, but now I'm finally getting to play with MIMO, I guess, now that I've moved on from Ettus research.
As you mentioned, the 2-meter EME, it's not really MIMO, it's the dual polarization. But we do have a dual SDR. They're both off the same LO, same phase. And then they go into, like I said, a bunch of LINRADs to try to do the processing. That's a very, it's not as smart a system as it ought to be, but it is trying to use the 2 receivers at the same time. Yeah,
and actually, I mean, with the same setup like that, you could, if you're doing terrestrial work, like MIMO wouldn't make sense for EME really, because there's no multipath. But if you were doing terrestrial work with with much smaller antennas, and but that same radio, you could do MIMO with the 2 channels, and you actually can do it with analog modes like FM voice, right? It's just like my friend's family car back in the day. You can do MIMO with those. It's of course much more common in digital systems and modern digital systems, but but yeah, I mean that's essentially a MIMO capable radio.
Quickie, is the Faraday rotation in EME equivalent to fading for linear antenna?
It's not, because it's a polarization effect. There's not really like, no matter what the polarization is, it gets rotated by that. If it somehow rotated, let's say, left and right circular polarization differently, and you transmit it on both left and right, then that would be sort of a diversity system. Now, terrestrially, there is some polarization diversity MIMO. The EME system really, I would say, doesn't fall under that. But for example, the newer base station, it used to be that like a cellular base station everything was vertical, because they figured, okay, your phone's going to be vertical. But these days, actually, the ones that have like 8 or 16 or 32 antennas, half of them are sort of diagonal one way and half of them are diagonal the other way. And they will effectively, polarization diversity is another, mechanism getting more out of the channel. So they will end up, if your phone happens to be vertical, it'll send signals to you vertical, and if someone else is horizontal, you can somewhat share the channel between them and send to them horizontal. But it doesn't necessarily think of it in terms of horizontal. The math just looks at them as channels, and the matrix math gives you the rotations and everything, and it just sort of does it automatically. But it is taking advantage of polarization diversity to allow more parallel usage of the channel. And phones these days, also, if you hold your phone like this or like this, you change the polarization as well. And someone else may be holding it differently, and now you're somewhat decorrelated, or your channel is somewhat separated from that other user, and you can be more efficient by sending essentially constructing 2 parallel channels using polarization diversity. Because they won't be perfectly perpendicular, it's like the more diversity you throw in, right? Even if any one metric of diversity is not sufficient to like double your throughput or something, when you throw them all together and add it up, it comes out to be this big win. So you have you'll have angle diversity, you'll have polarization diversity, you'll have frequency diversity by being on multiple bands, or frequency separated in OFDM within the band. You'll have time diversity by sending, sometime, and then that if the retransmissions are later, right? And so you add all this up and all these techniques together, and you get these much higher spectral efficiencies out of the system.
I have a little gadget up at Site 530, which will put one receiver on one ear and the other receiver on the other, or swap them or whatever like that, just by the Pro 3.
Yeah, and that I mean, if you're effectively doing the MIMO processing, in your mind that way, and I don't know, it's probably somewhere between equal gain combining and selection combining. You've got a neural network doing the processing. But yeah, I mean, you could also automate that if if there's some characteristic of the signal that can, that the processing can latch onto to sort of detect the parameters of the channel, it could then invert it, right? So if it's FM, it'll be easier, right? Because you have a constant envelope. Or if it's AM, it's easier. With SSB, it's a little bit harder, but it's doable.
I like what you said about the 2 transmitters. The part 97 says a transmitter has a maximum power of 1500 watts. Doesn't really talk about 2 transmitters.
Yeah, that's a good point. And the way it's sort of specified that way in like the Wi-Fi in the like ISM band regs and most of the cellular regs as well. And really what it's taken to mean is the total power from all of them. So and now I'm sure if you go and do this in the ham band, some old guy somewhere is going to say, oh, you can't do that. But really, the idea would be you split the power between the antennas, and the combined power has to just stay under the limit. But what you'll find is if you do this, you need a lot less power anyway. so it makes the communication much more efficient in the presence of multipath.
I had a comment. It's kind of a orthogonal to the goal here, because but when doing that HF diversity, where you have one antenna in one ear and one in the other, it also really helps to pick out like CW pileups, because you get spatial separation of the signals. They're not all collapsed on top of each other.
Mm-hmm.
Yeah, there's a very interesting aspect of brain MIMO, which is if you put a signal with noise into both ears and then run the signal down, you come to a place where you no longer can hear it or decode it. But if you put the same noise in both ears but the signal only in one, it actually goes down a whole lot further, many dB further. And so if you're listening with two radios to two separate frequencies, you actually hear things that when you go to concentrate with both ears, you can no longer hear it, which is really weird. But it's a well established. You know, there were experiments at Bell Labs many years ago that they couldn't figure out what to do with it, but it is very interesting. And so brain MIMO is that's a talk, a different day's talk. I really enjoyed this, by the way.
Well, thank you.
Matt, I'm working up at millimeter waves on line of sight paths, but I do have the ability to have two transmitters and two receivers. They'd be on the same dish, but two different feeds on the dish. So I can either use that to do beamforming to light up different areas of the dish, or change the tilt angle coming into the dish. I just don't know if any of this is useful, because I don't think I'm getting multipath on line of sight path, am I? Getting absorption fading probably.
Right. If you're not getting multipath, then that doesn't mean the second, you know, this sort of second path isn't useful, or the second receiver chain or transmitter chain isn't useful. It just means that you're not going to get diversity gain, because there's nothing to have diversity against. But you could still add the, you know, get the antenna gain out of it, or in your case, the, you know, point it differently. So that you're effectively sort of beamforming on the feed at that point. I
mean, I do hear fading. It's very slow. I mean, seconds or tens of seconds.
Right.
I'm assuming it's just moisture drifting across the path, but it could be changes in turbulence in the path too.
Yeah. So if it's that slow, my guess is that it's more of a changing absorption, or a I mean, I suppose it could be multipath, but typically multipath isn't that slow. I don't know, but Dave, you probably have a better idea. But I would say you know, I mean, it can be multipath, right? You can get refraction through ionosphere or troposphere and stuff, and might have multiple paths like that. But yeah, you know, anytime it's line of sight, you tend not to use the, you know, the MIMO techniques, and you just more look at beamforming.
Do you think beamforming would be helpful in that case, Stephen?
Well, so if you've got if you have two separate dishes, then yes. If you have one dish and you have two separate things in the feed, then it's more of a pointing rather than a right. You're not getting antenna gain, right?
Well, if I phase the two feeds, I can illuminate the top or the bottom half of the dish. So I'm using a fraction of my aperture, but a different, you know, I don't know if the path varies to the top of my dish versus the bottom of my dish.
It probably isn't that. That's more likely to be you're just pointing. You're sort of changing your pointing.
I mean, the dish is 200 wavelengths in diameter, so there is some difference between the top and the bottom, but I don't know.
Yeah, I mean, it's probably situation dependent, but yeah.
And frequency too. I think I've seen that at 10 gigahertz. The apparent source moves several degrees, and if it was somehow tracking that for me, then I wouldn't lose the QSO basically.
So thanks for the fantastic talk, Matt. And
thank you.
I really enjoyed demonstrations in GNU Radio. Because when I took our communications class, we basically learned BPSK was these two ideal dots, and it was really cool seeing how that actually differs in practice, where you have these point clouds that move around. I was wondering if you have any recommendations for resources for students to learn how to do all of the cool stuff you did in GNU Radio.
Well, there's a lot of example code out there for GNU Radio because it's all open source. There's I mean, there's a huge number of ham radio programs that people have written in GNU Radio as well. So there's a lot of example code out there. There's all the videos from all of the recent GNU Radio conferences are online on YouTube. There's, you know, the papers from the GNU Radio conferences. and of course the mailing list. So there's lots of folks there who are hams actually, including actually a couple who are local. We have a really good contributor who's interested in the various forms of TV broadcasting. He goes by the name Dr. MPEG, and he's somewhere in the Bay Area. He has implemented, DVB S and S2 and DVB-T and ATSC 1, 2, and 3. Right? He's very active, and he's a ham, I believe. But yeah, there's a good number of hams in the community.
Awesome, thank you. And I guess another tangential question I had was, so I did some research in speckle imaging, and so speckle imaging, it turns out, is basically the same math as multi-fading, because it's multi-path fading, because it's basically a multi-path for lasers where you bounce monochromatic laser light off of a rough surface. And one of the, in some cases, for some techniques, you actually want speckle, because you can do some analysis with the spatial correlations to get you information about the scene that you're imaging, even if the wavefront itself doesn't resemble the scene at all. But in other cases, you want to get rid of the speckle. So I've seen people use techniques like wavelength diversity to average out the speckles. So I was wondering if anyone does that with MIMO communications.
Yeah, and actually some of the more complicated MIMO schemes are really sort of effectively holography in a way, and the math is is very similar, and so yeah, so there is a lot of that. GNU radio, there's not much people doing with light on it. With radio, you can do a little bit more because you recover phase, whereas with light you don't recover the phase. Although the phase operates on but your receivers are just amplitude receivers. But yeah, a lot of the same concepts apply. And I do remember this was done by the folks at the Allen Telescope Array, which actually now makes extensive use of GNU radio. But the SETI folks up in Northern California, where they have like 42 dishes, they were using some really interesting holography techniques with their dishes, by using by scanning the dish across some known emitters. They were able to reverse out and compute the shape and all of the imperfections in their dishes, and they were able to demonstrate this by they put just very thin tinfoil of some letters on their dish and just pressed it down smooth, and they were able to get a picture of that through holography technique. So yeah, most holography is light, but it applies to all this, and it's all matrix math when you come down to it.
Hey, Matt, I had a general question, I guess, maybe on a tangent here, but for a lot of the stuff you presented, it was like very environment dependent to get like an optimal result. And there was like, maybe the one wasn't the optimal result, but it was the one that was applied. How does like a modern receiver go about choosing like in real time what might be the best way to implement this?
Okay, so if you looked at my flow graph, let's say if we use the one where it was with the Alamudi, where it was fading but still recovering the signal, the way it does that is there's some pilot tones in the signal, and so by looking at the distortion of the pilot tones, you're not, I shouldn't use the word distortion, I'll be more precise. The phase and amplitude of the pilot tones, you're able to reverse the channel. And so all of this stuff is really, it's sort of automatic, right? By tracking the signal and essentially equalizing the amplitude and the phase, you're able to get the optimum signal. But in the case of receive diversity, that's just what you do. Anything on the transmit side, it's typically you need to be telling the transmitter what the channel looks like, right? And so if you, for example, look at, I keep coming back to cellular, but in the cellular modes where it's using multiple, where it's beamforming towards the user, there's a significant amount of traffic coming from the user back to the gateway to the cell site to tell it, oh, this is better. Oh, the two phases you sent me, they're 87 degrees or whatever, and so it's reporting that so that the base station can then optimize the signal that it sends to you. So there's a tremendous amount of feedback going on, and in some cases it's more than, it can be more than 10 or 20% of the total rate is just like this overhead of channel training and things like that. So yeah, it's really, I was just demonstrating, mostly what I was demonstrating was open loop, except for that last one. But it really is a closed loop kind of system when you start to use transmit beamforming or these more complex modes.
Gotcha. Thank you.
Okay, well, thanks everybody for listening, and hopefully I'll get hopefully the meetings will be in person at some point, and I'll be able to come by and or go to the shack at some point. It's been a while since I've done either of those things.
Yeah, we look forward to having you, and thanks again so much for the fantastic talk.
No problem.
All right, have a good night, everyone.